So now we come to the most exciting question. Can Milan really sound better? What do you think? Have you heard rumors about Milan sounding better? Yeah? Heard that? Yes. Is it true? Yes. What do you think? So let's dive into it. We start with the very basics. It starts with analog-digital conversion. So we need to understand that when we have an analog continuous signal, we look at this in certain time intervals. Then we get a quantized signal. And then when we want to convert that back to analog, we need to be exactly at the same time intervals to recreate this sampled value. If the timing here is slightly different, we will have an error in the reconstructed signal. That's just the basic for any AD-DA conversion. Now, what is jitter? So in simple terms, when we do a AD conversion, we need a clock. So we have a clock signal that defines these time intervals where we sample. So on these edges, we take an audio sample. So now when we go through a digital system, doesn't matter if this is Dante, MADI, or AVB, we have a digital system. So we need to transmit that clock to the other end. On that way, we will get some error in that clock, and that's the jitter. And depending on how much jitter we have, that will influence the quality of our DA conversion. So how bad can that get? Here's an example where we did a measurement where we introduced artificial jitter of 25 nanoseconds, and we see that the noise floor increases from minus 130 dB to something around minus 80. So if we had this jitter of 25 nanoseconds, this would be the resultant noise. So we can show that jitter has a significant impact. Now the question is, how much jitter do we really have? You remember we say we do gPTP because it is the PTP protocol that gives us the best synchronization. Yeah? So that's why we want to have every endpoint and every switch being involved in the synchronization. And this is really as good as getting an accuracy of plus minus 40 nanoseconds. So if we just generate a signal based on that clock, we get plus minus 40 nanoseconds error. That's not good enough yet, right? So in addition to that, we will also have PLLs that damp the jitter even further. But it is important to note that every element in this signal chain plays a crucial role in getting the timing as good as possible. Now, there was an AES paper published. My colleague Morten Laaf was involved in that, one of the renowned experts for timing things and network stuff. And we did an analysis about what is the worst case that can happen comparing PTP version 1, PTP version 2, and gPTP. And of course, it now can get very complicated depending on the number of hops, but let's take an example of 6 hops. You can see that in the gPTP network, we get an error of 0.063 microseconds. Then if we look at PTPB1, that's the worst case, where we get 2,500 microseconds error in the reconstructed clock. So what does that mean for our audio signal? If we take an example where we look at a line array with 12 elements and we analyze the frequency response in some reference point here, then we can calculate how much error we get in the frequency response depending on the timing error. And this is the result. If we have a perfect clock, we have a very minimal error in the frequency response. So that's what we can achieve with gPTP. So here we take the error of PTP into account, and we get a very small variation here in high frequencies. If we take the worst case scenario for PTP-v1, which can practically happen when you have a heavily loaded network, you can get something beyond plus minus 6 dB error at 20 kilohertz, and it starts already rolling out here at 1 kilohertz above. You get a significant error in the frequency response. So I'm not saying here that this is always happening. Yeah? So when you have a stable network, you might be okay, but when a situation occurs where you load the network and you have a spontaneous thing going on with a lot of remote control data, this can happen.